Right? These are all important. How do you make junctions? So let's put all this generally together into fluid flow, like aerodynamics. That's a special formula. One of the key challenges in all fluid moving projects is to try to design a system that has the least resistance. Right? We want the fluid to go easily through the pipe. We don't want to have to push it very hard. It's better if we don't need a big pump. But there's a very precise science that we know a lot about, but not everything, about how to shape the pipes, how to connect them to each other, so that the stuff flows through as easily as possible. One thing that we've learned on the bio side of fluids, and by the way, put this one up here. Biofluids are very big. When humans have heart attacks or strokes, and that kills millions of people every year, right, all around the world, from a heart attack or from a stroke, usually it turns out that the place that had the problem was right behind a junction of some kind inside the body that created what's called turbulence. And turbulence is a waste of energy. So normally in the pipe, the fluid flows along. We talked about this a little bit the other day. Here's a pipe. If I'm pushing water or something through the pipe, at the very edge, it can't move. It's stuck to the wall. The atom of water is stuck to the wall atom of the pipe, and there's no motion. But the next atom over can slide a little bit past the first one, and the next one can slide a little bit past. So out in the middle, the water goes right through with very little resistance. But at the edge, there's a lot of resistance. So the design is to try to make this transition from where there's a lot of resistance to where there's no resistance, make that as small as possible. Well, if you have a splint, this fluid here comes along and it hits hard on that point, and it creates some turbulence like this. Right? The fluid has to kind of tumble around that point. If you have a heart attack or you have a stroke, chances are the problem was right in here. That tumbling blood starts to cause a damage, and then a clot forms, and it gets bigger and bigger, and now the fluid coming through there has to squeeze harder and harder to try to go through. And finally, because at the edge it can't move at all, finally the edges are so close together, not enough gets through. You have a heart attack. Or you have a stroke. What's a stroke? What is a stroke in medicine? What does that mean? What is a heart attack? I just said these two words. These are probably the two most common causes of death in the entire world. But what does it actually mean? What actually happens in a heart attack?
The heart cannot pump the blood.
And why can't the heart can't pump blood, and why not?
Because of something in the pipe, they get stuck.
Yeah, well, the heart is a muscle like any other muscle. And in order for the muscle to work, it needs oxygen. And it can only get oxygen from blood. So the heart has to pump its own blood to get back to the heart to get it oxygen. If you get a block and it cuts it off, then the muscle that receives that blood can't get oxygen. It can't work anymore. So the pump stops. That's a heart attack. Some part of the pump can't work anymore. If it's big enough, you die. What's a stroke? Yeah. But what's a stroke in medicine? Who knows what a stroke is? A stroke is the same idea, but in the brain. The brain also needs a lot of oxygen. So if part of the blood going into the brain gets cut off, that part of the brain will die. It doesn't get oxygen. And usually if you see somebody who had a stroke, some part of their body doesn't work anymore. Maybe they can't talk, maybe their arm, they can't use one arm, one leg, something like that, right? Because they lost the blood to that part of their brain, and that part of the brain died. So one of the big things going on in fluids research now in mechanical engineering departments, inside mechanical engineering departments, is investigating how can we make this better. So we talked a little bit about biomaterials. One common area of research in biomaterials are little artificial blood vessels. They're often called shunt. Have you seen this word? If you see this word talking about medicine, it's talking about a little piece of artificial blood vessel. So you come in with a knife, you cut this out, throw it away, and put in an artificial piece that's wide open again. That's the idea. Now, how do you design that artificial piece so the same thing doesn't happen all over again? One important thing to do is to change the shape and try to get rid of that bad flow that caused the problem in the first place. Make it somehow smoother. Okay, it's pretty interesting. Nature had 1 billion years to give us this body. In the last 5 years, some people think, I can make a better blood vessel. Nature's blood vessel has this problem. It turns into a block. And then I have a heart attack or a stroke. I'm going to take it out and put a new blood vessel in that I made. And it's better. It has a better shape. It's interesting. Does it work? Yeah, it does work. A lot of times. Not every time, but a lot of times. We can make an artificial heart, right? The idea of a heart, it's only a pump. Right? We know how to make pumps. We can make an artificial kidney. Right? What is the function of a kidney? You know, kidney filters the blood. It takes certain products out of the blood that are waste so that you can pass them out of your body. So it's a chemical process to pick things in the blood that should be outside of your body and take them out. We can build an artificial kidney. We can't build an artificial everything. Yeah. Okay. Anyway, so biofluid is another one. What's another really big one in fluid thermal sciences?
Gas.
Gas? Did you say gas? Yeah, gas, okay. How about I understand that Andy talked a little bit about hydraulics one day. But not everybody's in that class anyway. What is hydraulics? What are hydraulics? Yeah, hydraulic is when you use some kind of a fluid to transfer power from one place to another. It's a brilliant idea. And machines are full of hydraulics. They're full of them. Right? It's a flexible way of transmitting power. It's a great idea. So I can take a hose and start here and put the other end over on the other side of town somewhere. Right? And if the fluid I put inside that is continuous from one side to the other, then when I push on the fluid on this side with some kind of a pump, it creates pressure on the other side that can do the work that I want to do. So I can have, maybe on the other end, I have a nice piston, and at the end of the piston, there's a fist, right? So I can have the other end of the pipe go over to that guy's nose over there, and if I want to punch and push on this end, and the piston comes out on the other end and punches him in the nose. So that's not so friendly. But there's a lot of good ways of using hydraulics to transmit power. Right? Hydraulics are amazing. Now back where I live on a farm. And I have a tractor. And my tractor does everything with hydraulics. Right? That's not unusual. The motor on my tractor doesn't have very many mechanical connections to anything. What it has is a big pump. It creates a lot of pressure in that pump inside of a tank. And from that tank are lines that go to all kinds of different pieces of equipment. If I want to lift something up, weighs 1,000 kilograms. I pull a little lever, and what happens? There's no arm. What happens is there's a tube full of hydraulic fluid at high pressure. And the total force is the cross-section area, the area times the pressure. It's a great idea. We could lift this building. We could all do it together, right? If we had a big enough platform. We could do it with our breath. How hard can you blow? I don't know how hard I can blow. I'm just asking you. Maybe you know. But you can blow a little bit, right? So if you blow a little bit, you make a balloon get bigger and bigger. If you had a big enough balloon, you could raise this building. You could put the balloon underneath the building flat. Have the end of it sticking out somewhere. And if you have enough time, you create a little bit of pressure in that balloon. And that pressure spread over a big enough area creates a huge force. You can lift the whole building. No problem. Right? No problem. Okay. Well, hydraulics is a special kind of one of those systems, and the other one is called pneumatic. Okay? What's the difference between hydraulic and pneumatic?
Pneumatic use.
From glass?
And air.
I'm sorry, I'm not understanding you. I know you're saying it. Gas. Yeah, pneumatic has a gas, and hydraulic has a liquid. So normally a hydraulic has what's called incompressible. And pneumatic is compressible. What does it mean to be compressible? You can change the size. You can push on it and change the size. You know, I think one of the most amazing things in the world is water. Water is incompressible. So I'm also a scuba diver. All right. So you have on the Earth. Here's the Earth. We have all this air, and it all weighs a lot. And there's something like 120 kilometers of air pressing down on the Earth. Then you get inside the ocean. How far down in the ocean do you have to go to have the same amount of pressure added to 120 kilometers of air? How much water is that? Who knows? 10 meters is one more atmosphere of air. So 10 meters under the water, the pressure is twice. If you go another one, 20 meters under the water, the pressure is 3 times. 30 meters, the pressure is 4 times. What's the deepest point in the ocean? How deep? About 10 kilometers, right? So 10 kilometers is equal to how many times the air pressure? If every 10 meters is another time, what should I write in here? Alright, well you keep thinking about that one, but in the meantime, that's a lot of pressure. And the amazing thing is, the water is the same size at the bottom as it is at the top. It doesn't compress. Water is not compressible. It's not the only fluid, though. There are other fluids that are also incompressible. Incompressible means you can't compress them. So some of these systems that use fluid to transmit power, they use incompressible fluids. The advantage of that is, when you change the volume on one end of the system, the volume at the other end has to change by the exact same amount, no matter what the pressure is. So that makes it very easy to control the size of the motion. Okay. But some of these systems are compressible. Like air is very common. In a machine shop, if you go to have your car fixed or your motorcycle fixed, they probably have an air compressor. They probably use some air tools. What's the advantage of using air? Actually, for a lot of things, it gives you more control because it's compressible. It's like a cushion. So even though you put a lot of pressure on, it also kind of acts like a cushion. Sometimes that's very important. So sometimes it's better to have it compressible. The trouble with it being compressible is it's harder to have precise control. It's very difficult to have precise control. Because it's cushion. Exactly because it's cushion, you can't have precise control. So which one do you need? It depends on the job. Right? Sometimes you need precise control. Sometimes you need a cushion. What do you do if you need a cushion and you need precise control? If you need them both? That's why we have experts. Let me point out something really super important for you in your career. Most of the problems that we face don't have a single right answer. And that's a great thing if you want to make a career as a mechanical engineer. Because if everybody already knew how to do all this stuff, who would hire you? Why would they need to hire you? Why would you have a job if everybody already knows how it works? In fact, most of the things can always be better. Nobody knows how to make it perfect. Sometimes you need precise control, sometimes you need cushioning, sometimes you need something in the middle. Every problem is a little bit different. You need an expert that can fix this problem, and then fix the next one and the next one. You want to become that expert. That's your goal, is to become an expert. Alright, so any questions about these? There's another whole category of fluids and thermals we haven't talked about.
Can you explain why hydraulic is incompressible?
Why is it incompressible? Well, it's the things that are, the fluids that are incompressible. So that's just a property of the fluids. That's a physical property of the fluid, right? That's science. Humans did not invent water. But what we discovered about water is that it's incompressible. It turns out there are some other fluids too that are also incompressible. So that's a science property of the water. Now what do we do with it? That's an artistic idea of an engineer, to turn that incompressible fluid into a system that we call a hydraulic system. Okay? Most hydraulic systems don't use water. They use a different incompressible fluid. Why? Why don't they use water? Water is not compressible. No. That's not the problem with water. There's another problem with water. Water tends to be a problem with corrosion. So there are other fluids that work just like water. They're also incompressible, but they don't have the same problem with corrosion. Also, inside of every fluid, there's friction. Right? And friction uses up energy. Some fluids have more friction, some fluids have less friction. What's a fluid that has more friction? Well, something that has more friction than water, name one. Well, oil, right? How can you tell when a fluid has more friction? Because it goes slower. If I take a fluid that has very little friction, very low friction, I pour it on the floor, right? Because the fluid doesn't want to sit like this. It wants to sit like this. So how long does it take to get to this stage? It depends on how easy these molecules can slide past each other. They're all trying to get to the bottom fast. But if they can't slide past each other very quickly, it takes a minute. How about honey? Honey has a lot of friction. You know, everybody knows what honey is, right? Yeah. How about beer? Probably not so much, something like water. Some fluids have less friction even than water, and they don't have corrosion. Those are ideal fluids for hydraulics. Very low friction, no compression. Perfect. Okay. that you didn't even think of yet? I'm going to write an acronym. You know what an acronym is? Does everybody know what acronym is? Okay, acronym is equal to a word made usually from the first letters of a phrase. Like, for instance, USA. That's an acronym. What's USA is an acronym for what words? United States of America, right? We did APAC yesterday or a couple days ago. That's an acronym. ASME. That's an acronym. Okay. So here's the acronym for this category. What's HVAC? Huge business. Huge business. I can tell you that we are all benefiting at this very moment. All of us are benefiting from HVAC. Right now, look around. HVAC is going on right now in this very room. Heating, ventilating, and air conditioning. Huge business. Especially, we all think about it in our private lives. You go home at night, you want to have a fan or maybe some air conditioning or something like that. In the wintertime, you want some heat. So it matters to you in your private life. But it's an even bigger business on a commercial scale. If I build a factory, I have to get fresh air inside the factory, especially if there's some chemical process going on. Right? I have to control the heat. I have to control the air quality. If I make a hotel, if I make a department store, a big store, right, airport, you name it, I've got to control the air quality. Think about an airplane. What a critical, important thing this is in an airplane. Who knows when the airplane is flying at a normal altitude, what's the temperature outside of the airplane? Yeah, it's usually something like that. Okay? So if you don't have good HVAC on the airplane, what happens to your passengers? They're all dead. If they're dead, they're not going to pay you. It's not good business. Also, what's the altitude of a normal airplane when it's flying? Something like 10,000 meters. It's not enough oxygen to even breathe. So even if they didn't freeze to death, they would die from no oxygen. So you can't have an airplane without excellent HVAC. It's life or death. Life or death. Now, down here on the surface, it's not always life or death. But in a big factory, it could be life or death, depending on what they're doing. Maybe they're painting cars. If they're painting cars, you have to control that air. If the worker breathes the paint, he'll die. If I want to have a mine, and dig a mine and get some valuable material out of the ground, I have to have a good HVAC. So this is really a huge business. Heating, ventilating, and air conditioning. Comes under the fluid thermal. Okay, can you think of other things up here? Well, we could write some again, smaller pieces. For instance, underwater, we could talk about agricultural irrigation, right? That's very important to help feed the world. We could talk about Treating sewage. What happens with the sewage from the city? You know, when 1 million people go to the bathroom, what happens to it? So you need a big treatment center to clean that before you put it back into the environment. So there are lots of sub-pieces that go under the fluid and thermal part. All right, let's move on for a minute. Dynamics in motion. K44s, you just took dynamics. What are some of the subtopics that you might study under dynamics?
Energy. Motion.
Yeah, motion, right? So everything about M equals MA. Mechanical engineers love cars, trucks, buses, submarines, airplanes, helicopters, motorcycles. Help me out, what else? Trains, right? We love that stuff that moves around. We love that. All of it involves some dynamics. Machines. Machines always are moving. Robotics. Hot topic. This could be electric or other kinds of machines, hydraulic. What else can you think of under this category? Vehicles, okay. I'll just say vehicle dynamics. Vehicle dynamics is a specialty topic all by itself, especially for things that fly. Right? What's the difference between things that fly and things that roll along on the surface?
Fly deal with traffic. First, move on the road. We need to deal with friction.
Yeah, I think things that move on the road, it's usually one-dimensional. Right? You go forward and backward. I mean, you can turn, but even when you're turning, you're still kind of going along one line. But when you're in the air, the rotation comes in. That changes everything. It makes the dynamics much more complicated because it's three-dimensional. So, for instance, in a car, when I press my foot on the gas pedal, the power in the engine spins the drive wheels, and it just pushes the car forward. But in an airplane, I could be flying along and suddenly turn the airplane, and when I push on the gas pedal and the engine fires, it's not even firing in the same direction the plane is moving. The plane could be skidding sideways because it's crosswind or something like that. It could be upside down if I'm a bad pilot. The plane could be in any kind of orientation. It's not vertical, not horizontal. And so it's not, the force that I apply is not in the same direction as the way I'm moving. It's a lot different from the car. Anyway, vehicle dynamics. What other kinds of things can you think about? I'll write one. This is a really big one you might not think about, but yeah. Because we love stuff that moves, and a lot of things that we build have a cyclical motion, as we've talked about. Right? Whether it's a car engine, car wheel, a turbine engine, some robotics, whatever it is, it has a rotation. And if you get a little bit off center on the rotation, it creates a big side-to-side force. Okay? In dynamics class, did you have curving linear motion? If here's a center, and I tie a string to a rock, say, and I spin it around, then the rock wants to fly off in that direction. To keep it spinning, there has to be a lot of tension pulling it this way, to pull it back to keep it in a circle. Otherwise, it just flies away. Right? And we figured that out a long time ago, because you can spin a rock around, and then let it go, and it's a weapon, right? Throw it at something. So as soon as you let go of the string, it flies in a straight line. But when you're holding the string, you're pulling it towards you. So this keeps pulling in towards you. So now let's suppose that you have a wheel. Here's the wheel, and I'm driving down the highway. The wheel's spinning around. Every little piece of mass on here is like that rock on the string. Every piece is like a rock on a string. What holds it together? There's a force that pulls towards the center. Now, if I have the mass well distributed all the way around, all of those little pieces of force all the way around cancel each other. So the net force, the sum of all those forces is 0. And so there's nothing pulling on the axle, and the wheel spins nice and smoothly. But if it gets a little bit out of whack, maybe I have more mass on this side than on this side, the way I've drawn it. So now there's a lot more force pulling that way than this way. And so it pulls the axle that way. But then when the wheel rotates, it's pulling it this way. And when the wheel rotates around here, it pulls it this way. So as I roll down the road, the axle gets pulled all around. And everybody in this room, I'm sure, has ridden in a vehicle that has this problem with the wheel. And it's pretty uncomfortable, right? It's terrible. So in the case of a car or something like that, it's just annoying, right? It just makes you mad. But if this is on a precision piece of equipment, like in a factory, maybe you can't tolerate it. Maybe you can't produce the product you're trying to produce because this isn't reliable. If this is a saw and you're trying to cut a piece of metal, a precision piece of metal to make an airplane, but you don't have the saw balanced, you don't have the weight right, you have too much vibration. Instead of cutting a straight line, it cuts a jagged line from the vibration. You can't build an airplane. You can't do it. You can't build a submarine. You can't build a bus. So vibrations is really a big, important issue for a lot of mechanical engineering. Okay. What else in dynamics of motion? Say again. Impact. Thanks. Impact. Yeah. Impact would be good. Don't worry, I can't hear very well in English either, so it doesn't. Okay, impact. What else? Another topic in dynamics. Or motion. Well, we said machines, and we could break that down farther and farther. We could talk about putting power into the machine. Talk about just designing the pieces of the machine so that it can operate, so everything moves. If you've ever taken something apart, a complicated piece of machinery, it's amazing how many pieces there are usually, right? They can have a lot of little pieces, and they all have to have a very precise shape, very precise geometry in order to move. If something gets a little bit bent or a little bit distorted, the whole machine can lock up and it can't even move anymore. So a big thing inside of the dynamics is to make sure that when you design the machine, the pieces can be produced so that it moves, so it really does move. Okay, well, let's see here. Let's move on to math for a minute. What kinds of topics inside of math? Okay, well, I'm going to start one with CAD, another acronym. Who knows what CAD is? Computer aided design. Good. finite element. Who's heard of the finite element method? Has anybody heard that? Okay, the idea behind finite element method, it's a potentially brilliant idea if you do it correctly. So here's the idea. The idea is that a lot of physics is extremely complicated, especially if you try to analyze the whole thing at one time. Right? The thing you're trying to analyze. So the idea with the finite element method is pretend that the whole system is made up of a bunch of little pieces. And then the behavior of the little pieces is very simple. Each one is simple. So I can create a very simple model of a small piece. Okay, we're getting a little too loud. Everybody, let's go. Thanks. So I'm gonna take the whole big piece, the whole big system, and break it into little pieces. And the little pieces are simple enough that I can make a simple model that's accurate for them. Okay? So let me give you an example. Suppose that I'm going to calculate an integral. What is an integral? It's a sum of what? It's the area under the function curve, right? So if I put, say, f of x, and here's x, and the function looks like this, the integral is equal to that area. Well, I can calculate the exact integral if I'm a smart enough mathematician, right? I'll figure out the integral of f of x dx, and maybe I know what it is. Like, if f of x is sine, what is the integral?